Thanks very much for coming, everyone. It's my pleasure to introduce the speaker, who is Mikel Sanchez-Garitaonandia. So Mikel did his PhD at the University of Barcelona together with David Mateus, and currently he's a postdoc at the Ecole Polytechnique in Paris. Please, stage is yours.
Okay, so thanks a lot for the invitation. I'm actually very excited to talk to you.
Oh, you can mute.
No,
Mute no, el sonido.
está muteado.
No,
Sí, está muteado. ¿No? El micrófono.
sí, el micrófono.
Está muteado.
Porque try speaking again.
Hola.
It seems to be fine. So, sorry about the technical problem. It had never happened before.
No, it looks like I have everything on.
Yeah. Okay. Yeah. Then you should. Let's try again. Maybe.
Okay. Okay. So sorry about that. I'm very excited to talk here because the numerical code that allowed us to produce most of the papers that I'm going to talk about today precisely started here with two collaborators at the Gravitational. So today I'm going to talk about gravitational waves that would come from first order phase transitions in the early universe. I will go into detail in that. And I will use as a tool holography, and I will also explain what that's about. So let me start by putting the faces of the people that made all of this job possible. And in particular, these two faces that are probably familiar to most of you, that unfortunately are not here anymore. But well, with these two guys is where all the numerical code started, and all the things I'm going to talk about today are possible. And of course, the help of the rest of the collaborators is, well, you cannot measure the help. So let me start with the physics. So as you know, in 2015, we discovered for the first time, well, we detected for the first time gravitational waves coming from a black hole merger. And this basically implied that we have a new way of testing or studying gravity. In particular, now we have access to a strong gravity regime, as most of you know. But in this talk, I'm going to be focused on a different part of the equations, which is that I'm going to try to use these gravitational waves to learn about matter, due to the fact that any source of matter, any source of energy, is going to couple to gravity and can potentially lead to emission of gravitational waves. So this means that we have new ways of learning about matter, and opens very exciting doors, because now we have access to astrophysical laboratories, okay? Matter in certain conditions that are difficult to achieve in Earth, but are somewhere out there. And the way to access the physics there would be by detecting gravitational waves, like, for example, neutron star mergers. And we can now also observe farther into the past than by using light, as you all know. And therefore, we can access what were the conditions of the fluid that is filling the universe at the times earlier than the CMB, for example. This is, in fact, a golden opportunity for two things that are related to what I'm going to talk about. First, we can learn a lot about QCD in extreme conditions. As you know, QCD is very hard to tackle due to the strongly coupled nature. And actually, this is the phase diagram of QCD, but it's mostly hypothesized. The only things that we know is what happens at very low baryon number, and also what happens in this range where nuclear matter undergoes a small, well, a first order phase transition. But the rest is basically unknown, like this kind of questions might suggest. And now in neutron stars, if we detect gravitational waves from them, as we did already, we can get access to how does the phase diagram look in this area? How do the properties of QCD look like in this area that is difficult to access otherwise? And also, looking into the past, we have a very unique chance of discovering physics beyond the standard model, in particular by detecting gravitational waves that come from first order phase transitions in the early universe. And I'll also talk about that quite a lot. So the plan of the talk is fairly ambitious, okay? I will start by giving a very simple review on dynamical realization of first order phase transitions to put everyone in the same page and to explain why gravitational waves coming from here could be detected. Then I will present the tool that I'm going to use in order to reproduce our results, which is holography, and the setup we use. Then I will talk about bubble dynamics, basically something that comes from first order phase transitions, as we will see now. And then I'm going to talk about the very exciting paper that we put out a couple of weeks ago about a possible new signal coming from neutron star mergers, also in the context of bubble dynamics. So this is what at least I want to achieve to explain today. And then if time permits, I will talk about a possible alternative mechanism of gravitational wave emission in first order phase transitions in the early universe. And finally, I would like to talk a bit about weak cosmic censorship and Gregorian instability. And please, if there's any questions, just interrupt me anytime. So let me start by explaining the dynamical realization of first order phase transition. For that, let me take a very generic phase diagram of a theory that has a first order thermal phase transition. So what you're seeing here is what is the energy density of different states as a function of the temperature of the system. And as it is usual in these kind of theories, what we have is that there's a region, a range of temperatures, where for a given temperature, we have multiple accessible states. Okay? This is what triggers the phase transition. If one analyzes the thermodynamics, you can distinguish between which one of these states are preferred, which ones are metastable, so they are locally stable but are not preferred, and which ones are unstable. In particular, for very high temperatures, we get that the high energy branch is where our system would like to be. But then there's some critical temperature in which we switch preferability, and the states that would like to live at low temperatures are low energy. In between, we have this set of metastable states that are locally stable, but at that temperature, there's another state that is the one that is globally stable. And then there's a set of states that have negative specific heat. You see that if I heat up increasing temperature, these states, the energy goes down. That's quite unusual. And this is going to be related to dynamical instabilities. Maybe I have time to talk about that. So it's going to be useful to think in terms of an effective potential. Effective potential is basically a function whose extrema tell us about the equilibrium phases of our system, and it also tell us how they are connected on phases. So for example, for a theory that is electroweak-like, standard model-like, we can plot the effective potential as a function of something that allows us to distinguish between phases. For example, you can take the VEV of the hits. And going back to our diagram, if we are at very high temperature, okay, so this would be a very early universe, very hot. You see that there's only one state that is available for the system, and therefore the effective potential has a unique minimum sitting here. If now we lower the temperature slowly, which would be representative of what happens when the universe slows down because of expansion, right? So cools down because of expansion, you see that at some point the universe will be at a temperature that has accessible more than one state. Therefore, the effective potential will have two minima corresponding to this state and this state, and a maxima in the middle corresponding to this unstable state. At precisely the critical temperature, both minima of effective potential are going to be equal in height, meaning that the state doesn't really care in which state was to be. And then below that, the preferability changes, and the effective potential, well, the one that was a local minima, but not the global one, becomes now the global minima, and the one that was before the global one now is just a local one. This is basically the fact that we go from this high energy branch to this lower energy branch. Okay? So this was very basic, but this way we're all on the same page. So now imagine that I take a universe, okay? We have some theory beyond the standard model, and it's going to be cooling down because of the expansion of the universe. Therefore, it's going to be sitting at the beginning in the preferred state of that temperature. And as the universe cools down at some point, it's going to hit the critical temperature and dip itself into the metastable. In terms of effective potential, this means that now our universe is going to be trapped in this local minima, while it would like to be. Classically, there's no way to go from here to here, but we have fluctuations due to the finite temperature in the system, and there's a non-zero probability of fluctuating from this state to this state. And this probability, as you know and you're familiar with, is exponentially suppressed with something that I'm going to explain now, which is the action of the critical bubble, which is a representation of the height of this barrier. And I will go now. So what is a bubble? A bubble is basically a patch of the fluid that was in the metastable state, in which we have nucleated the stable one at the same time. And these two states are going to be connected through a wall, which is this green area that you see here, that smoothly connects the interior with the exterior, okay? This is an equilibrium situation because the state inside is preferred over the state outside. It has greater pressure and therefore the walls want to expand because the system inside is pushing, but there's a surface tension associated to the wall that wants to compress it. And there's a precise equilibrium of these two things. This is equilibrium, but unstable, because when I match precisely these two sources of force, in the moment that I deform a little bit my system, either it will want to grow indeterminately, or either it will want to collapse because of the surface. Okay? Questions so far? So what happens in the early universe? Once our universe got into the metastable branch because it cooled down below critical temperature. Yes. Yes, the instability time scale is of the order of the temperature. So, well, we have here, once you're in a state like this one, and you want to nucleate down, you get a critical bubble, some bubble, and the time scale of the instability is basically going to be related. It's going to be an order 1 times the temperature, unless particular situations. But in general, you expect it to be a number times the temperature, no, order 1 number. So it's a microscopic rate instability. So in the early universe, what we get is that this bubble nucleation will happen in many places once our universe has cooled down below the critical temperature. And some of them will collapse, but some of them will start to grow. As they grow, because the growth is going to be spherically symmetric, there's no gravitational wave radiation. But because there's more than one, at some point they're going to start meeting each other. You can see in this medium picture. And they're going to start colliding and breaking this spherical symmetry. And gravitational waves are going to start being emitted. You see that at later times, once all the bubbles seem to have disappeared, in this case, they have almost disappeared, what you're left with is the stable phase, but highly perturbed. You see, this is highly inhomogeneous. And these perturbations are going to live there for a very long time. They're going to, let me say, this can be understood as sound waves. So these sound waves are going to collide with each other, and these collisions will produce gravitational waves. Yes.
Is unstable, and if just a single bubble, as it grows, why should it grow spherically?
Why should it grow?
Why should it grow and maintain that spherically? Have a population that violates spherically, so the three of them just get lost completely, even for a single bubble.
So the dynamic, one thing is, so the instability tells you about whether the bubble wants to grow or collapse.
Yeah.
The fact that I consider an initial bubble that is spherically symmetric is simply due to the fact that any other bubble is exponentially suppressed in probability of nucleating with respect to this one. This is the one that costs the least. Once it starts expanding, there can be fluctuations that make it slightly non-spherically symmetric. But what you can prove is that the dynamical evolution will fast retake you. So let's say the stationary state of expanding bubble wants to be spherically symmetric again. So you can deviate slowly, but you will always go back to spherical symmetry. Yeah. Where you have great departures from a spherical symmetry that persists is when you have collisions. Yeah. So let me emphasize that it's very important that these bubbles nucleate at a size that is very small, it's thermal scale, okay? But they are going to grow to macroscopic sizes. In fact, they're going to be a couple of order of magnitudes below the Hubble scale. The highly perturbed state at the end is going to contain sound modes or perturbations that are very long-lived. In fact, the life or the medium life of these perturbations is going to be comparable to the Hubble. is this fact that we go from microscopic to macroscopic scale and times that allows us to actually produce a significant amount of gravitational waves that are potentially detectable. Okay. And let me emphasize also that first order phase transitions inevitably lead to departure from equilibrium, which is what you want from the ground. So who is the one that takes me from a microscopic scale to a macroscopic one? Who's the one that takes me from bubbles that are very small to processes that are a phase transition at the end in something very microscopic? It should happen at a very local scale and very fast in time. So who's the one that is connecting this to that? That is precisely the nucleation. You see that this is the probability of nucleating a bubble per unit time and volume. And you see that there's a first factor that is just temperature to the form. It's the microscopic rate, but then you're largely suppressing it with this exponential of the action of the critical bubble. Okay, so the fact that it's very hard to nucleate things is what is going to take us from microscopic to macroscopic. So what do we know about the gravitational wave emission in such scenarios? There has been quite a long line of research on doing simulations of such bubbles by using effective methods. And it has been hypothesized and quite well tested that the gravitational wave emission is going to depend in a few amount of parameters. Namely, the transition strength, which is a measure of how much energy is released in this phase transition, the latent heat, if you want. What is the temperature at which it happens? What is the probability of how efficient is the nucleation of bubbles, which would determine how many bubbles are going to be in the system? And finally, how fast these bubbles expand. Because let me emphasize that these bubbles do not expand against vacuum. They expand against a thermal fluid, and therefore they're going to feel a friction that will, in principle, set a terminal velocity that is going to be smaller than 1. This is crucial. The challenge in computing these quantities goes from left to right. These are quantities that in a quantum field theory are fairly, let me say, simple to compute. They are just equilibrium properties. Then the nucleation rate is not trivial, but can be done. And then the wall velocity is an out of equilibrium property of the quantum field theory. And this is very hard to tackle with conventional methods, even at quick up. So this gives holography a very nice chance to be useful as a perfect lab to study out of equilibrium problems in quantum field theory from first principles. And the spectrum that people expect to get that could be detected by LISA, for example, from an electroweak like phase transition, it's something that is what is called a power broken law. So you have that this branch of the signal and this branch of the signal is scaled with a given power of the frequency. And then there's a peak frequency that can be very easily estimated by knowing what is the size of the bubbles at the time of collision, which is going to be the determinant scale that gives rise to this gravitational waves. Okay. And why do I say so far constantly beyond the standard model? Because in the standard model, there's 2 candidates to have a phase transition. The first one is the QCD, the hadron quark matter transition, or confinement deconfinement, which would happen at temperatures around 200 MeV. But the problem is that at the low densities the early universe was, we know from lattice QCD results that what we have is a crossover. We don't have a sharp phase transition. And therefore, the universe would have cooled down around this temperature, completely smooth. The other candidate, of course, is the electroweak theory itself. When we go from the Higgs phase to a symmetric phase. However, once you take this system and you study it at final temperature, the electroweak theory, what you see is that at the mass of the Higgs that we measure, what you have when you heat up your system is that you never truly recover the symmetric phase through a phase transition. It's a smooth change. And at asymptotically high temperatures, you recover the symmetric phase. So the cooling down of the system of the universe, according to the standard model, is completely smooth. So if we ever discover gravitational waves by LISA, coming from a first order phase transition, has to be something beyond the standard model. So it's a very nice opportunity to directly observe new physics. Yeah. This is the baryonic chemical potential. It's a measure of how many, the density of quarks that you have there. Yeah. So in the universe, we will have very low chemical potentials compared to the temperature, so you're very close to this axis, and that is usually shown. It's one of the few things we know that at very low chemical potential, we have a crossover, no phase transition. Yeah. Okay. So what kind of new physics should you have in mind? You can think about just minimal extensions of the standard model. It looks like if you take the standard model and minimally extend it, it's fairly simple to get a theory with a phase transition whose temperature is going to be, it's a minimal extension, is going to be close to the electroweak temperature. But you can also go beyond and think about completely new theories beyond the standard model whose temperature is below the Planck scale. Okay? And in principle, all of this is accessible if you have the adequate detector. Okay. Any questions so far? Okay, so let me introduce what is holography and what is the setup that we use. So for the purposes of this talk, holography is just a duality, which is two theories that explain the same physics, in which on one side we have a quantum field theory living in Minkowski in d dimensions. We're going to take it to be 4. That in the limit of a large number of degrees of freedom, this could be, for example, if you have an SUN theory, it would be the n there, the rank of the gauge group would be very large, and also very strongly coupled. Then this is dual to a classical theory of gravity in a funny spacetime, which is asymptotically ADS, and in one extra dimension. So the goal would be that one can map a problem here, that is very hard to tackle, to a classical gravity problem, solve it, you translate it back to the quantum field theory, and you answer the questions that you wanted to answer. We're going to be interested in dealing with thermal states in this quantum field theory. And one can prove that this is dual to considering black holes in the gravity side. Yeah, because black holes are the objects that have temperature from the point of view of gravity. And now, if we want to consider out of equilibrium problems of thermal states, imagine that I have a thermal state and I perturb it somehow, I gather a lot of energy in some specific spot. This is dual to having a classical horizon that I just perturb, like for example, I add some sinusoidal perturbation or something more aggressive to the horizon, and then the classical dynamics that is going to happen after that is going to be mapped into how does my quantum field theory behave. Okay, so what we do is solve Einstein's equations numerically in time with the correct asymptotic, and then we read what is the answer in the quantum field theory. Okay. So the model we use is something that is called bottom-up. It's a toy model basically that we capture a property that we're very interested in, which is first-order phase term. So in the gravity side, which is 5-dimensional, because we want a 4-dimensional thing, we consider gravity plus some sort of matter that is going to give us a phase term. And the cosmological constant to give me ABS is hidden in this potential. Okay? This is going to be dual to some CFT, so some theory that has no scales at all, that has been deformed by an operator that introduces a single energy scale. Okay, and this single energy scale is what allows us to have a first-order phase transition. You cannot have that if you have just a conformal field. And well, the potential that we choose for the scalar field in the bulk in the gravity side is very simple. It's some polynomial with 2 pre-parameters that allows us to adjust the system to have phase transitions or not. So this is not inspired on anything more than simplicity, and that it gives us what we want, which is a first-order phase transition. Okay. And if you're curious, it looks like it's a potential with 2 extrema, and the scalar field that is in our theory will be confined to this.
There's no barrier.
Sorry?
There's no barrier to realize phase in some kind of a barrier.
You mean that you should see another minima somewhere?
No. Yeah.
No, because this is the potential for the scalar field in the bulk. So the phase transition, how it happens in the field theory is very obscure from the point of view of the bulk. You cannot infer that there's going to be one by just looking at this, because the phase transition is not going to be about how does the scalar field want to configure, but how does the scalar field plus all the geometry want to configure itself. Okay, it's a bit more obscure. It's not trivial, actually. This is a question that we always have in mind. Can we cook up something that just by looking at the theory in gravity tells us that it has a phase transition? And the answer is that so far, we don't know how to do it. But we have a good starting guess that works. And you can always do the small deformations of things to get other theories with phase transitions. So the way that we do the numerical simulation is, this is a Penrose diagram for the asymptotically ABS spacetime. So we work in characteristic formulation. So we start by giving data in an infalling null slice. There's a horizon somewhere in our problem because we have finite temperature in the boundary. And what we do is give initial data and evolving time with characteristic formulation. And in order to avoid problems inside the horizon, where there could be large gradients, we just choose some radial cutoff beyond the apparent horizon. That is something that we track in our evolution, so that we get rid of part of our domain of integration so our numerical domain gets rid of part of the physical domain where all large gradients would be allocated, and then we avoid numerical issues. Okay. Okay. So is there any questions so far? Okay. Then let me go to the dynamics of bubbles. And what I'm going to present are the results of two papers. So I said that computing the wall speed is a very complicated thing in traditional quantum field theories, but with holography it's fairly simple once you have the code to do it. So there's no fundamental problem about it. So the way that you can very easily extract the velocity, the terminal velocity of a bubble that is expanding, is simply by hooking up initial conditions so that you consider a horizon that is dual to a state in the metastable state. So this would be filling our whole domain. And then in the middle, we take out a hole and we put, smoothly interpolating between this and this, we put a state which is preferred at that temperature. If this bubble is big enough, then the simple fact that the pressure inside is bigger than outside should do the job, make the bubble expand. Some stationary state should be reached quite fast, and you could extract what is the velocity. And you could do this for any temperature here, and for any kind of initial condition, you can play it. So if you do that, you get a simulation. So as I said before, this wall, this bubble is expanding against the fluid. So you say that it's heating up whatever that is in front, and that is the source of friction that will make the bubble to expand at a constant velocity. If you repeat that process for several initial states, what you can do is plots that are very difficult to compute by traditional methods of what is the wall speed as a function of possible combinations of equilibrium properties that could suggest some sort of simple relation between such a complicated thing and something that can be extracted from thermodynamics. In particular, we found some possible linear relation between the speed and what is the pressure jump in the bubble divided by what is the energy outside the bubble. So this is reminiscent of driving force divided by the resistance to movement. Also, you can find very easily that the latent behavior of these bubbles is completely set by what is the temperature outside, what is the state in which nucleation happened. It doesn't depend at all in the initial conditions. These are forgotten very fast. And then the question that we pose is, okay, this was true for a holographic theory, but is this universal at strong coupling beyond holography? And also, could it apply beyond and therefore could be useful for example, electroweak or minimal extensions of the standard model, where it's very present to have exact results for the next generation of the topic. You can also go beyond this, and you can start the simulation with two bubbles and simulate a collision and see what does holography tell you about. So as you can see, the dynamics changes completely, of course. And then at some point, this one inner wall disappears, and you would end up with a single bubble expanding with a fluid that is fairly perfect. Let me emphasize that this is not based on any effective description like it happens for the simulations or for the pictures that I showed you before of the bubbles. This encodes all the microscopic physics, all the quantum physics that there is in our theory, and we could test hypotheses like how true is it that hydrodynamics applies, which is what is used in other kind of simulations, or we could test other kind of assumptions. You can also find the critical bubble, which is what is precisely the bubble that would nucleate and tells you about how many bubbles will be in the system by simply playing with the initial radius of the bubble that you choose. For example, this is a simulation in which we chose two bubbles, one with a slightly bigger radius than the critical one, and one with a slightly smaller radius than the critical one. The way we found the critical radius is simply by playing. So it's not something we knew a priori, but by testing or by running many runs, we can do it, and you get something like this. The one that is slightly above the critical radius starts expanding. The dynamics is slow because you're close to the critical bubble, and the other one ends up collapsing, and the end state is just a homogeneous state where there's no trace of the initial bubble.
Yeah, the expansion of the bubble usually fast on Coulombic expansion at the same time.
Yeah, the expansion of these bubbles. So what happens is that
we compare with it also compared to maybe expansion bubble is slower.
as long as the temperature is not too close to the Planck scale, that will not happen. I can argue more in the details if you want, but at the end it's just a ratio of the thermal scale with the Hubble scale, which has a Planck mass suppressor with respect to the temperature. So as long as these two are not comparable, then you can assume that in the moment that these bubbles nucleate, they happen in an instant, and the dynamics of the universe is freeze. Yeah. What matters the expansion of the universe is for the post emission, which is the important part, which is once this bubble disappears and I have this highly perturbed state, this is going to radiate for a Hubble time. There, it's important. But for this bubble story, okay, it doesn't matter. And let me emphasize that the critical bubble action is very important to see exactly what point in this branch you're going to nucleate, given some expansion rate of the universe, and that it also gives you exactly how many bubbles you're going to have in the system, how big are they going to be, and therefore sets the characteristic frequency of the peak. So it's very important to have a detailed description of this action. So now, before jumping into a different topic, let me say what are the kind of things that one can do in the future, thanks to holography again, is that from all the parameters that I told you before, that the spectrum would depend on, I didn't say anything about the speed of sound, but I said something like sound waves. So I said that emission is assumed to depend only on the wall speed, what is the transition strength, how much, basically how much energy is released in the transition, and what is the temperature at which it happens, apart from the nucleation rate. So the reason why the speed of sound is not typically included is because if you take the standard model, most of your particle spectrum is very relativistic at the temperatures of interest. And therefore you can see, for example, in this plot, that how much does the speed of sound depart from the conformal value, 1/3, is very negligible. However, this in principle is not going to be true for other kind of theories. For example, strongly coupled theories where there's a unique scale set in everything. Like QCD, for example, it could be in neutron star layers, as I will go later. And holography naturally gives rise to speed of sounds that are far away from 1/3. As you can see, for example, in this plot, which is the speed of sound for the phase diagram that I showed you before. So you can see the speed of sound covers values that are very far away from 0.3, that's 1/3. Okay, questions so far?
So, when you're using this mapping for duality, if you hit QFT, you say, okay, that's the one, I love that one. Can you then, is there like a unique answer for what would be the gravity to that?
Yeah,
and
so
can you also get that? Right? Can you get that and say, okay, yeah, yes, now I can do the with that one.
Yeah, so in principle, not every theory, quantum field theory, needs to have a gravity dual, a gravity description, in principle. And it could be also that one may think that there exists such a dual, but it could be in a regime that is not classical gravity. Yeah.
Is it, I'm a complete outsider, so is it clear that, like, rigorously, any QFT has a gravity dual?
No.
Right, okay, so it's like, there's evidence from numerics.
There's evidence, there's also evidence for, there's one very well established duality, which is n = 4 super Young Mills with, at the end, it was type 2D string theory in ADS spacetime, which in the correct limit is just classical gravity. You can have the formations of both sides, and then you can imagine that it's simple to get other theories with these dualities. But then what there is a general belief that this has to extend to other kind of quantum theory. Yeah. But if you pick a specific one, it could be that it doesn't have a dual, or it could be that it has a dual, but it's in a regime in which I cannot use classical. Yeah.
And maybe just to follow up on that, you're always solving GR on the relative side. Is that also the correct thing?
That only means that what I'm imposing into the quantum theory is that it's strongly coupled and has a large N limit. So I'm considering a large number of degrees of freedom in my quantum theory, and then they are very strongly interacting with each other. Okay. That's what I know about the dual theory. Yeah. Okay. So now let me switch slightly gears. I'm going to talk about Bible dynamics, but in a different context, which is going to be neutron star. And I'm not going to use holography here for absolutely anything. Okay. So recent neutron star merger simulations have shown that in the merger dynamics, there's spots that are here represented by dotted lines that would undergo a first order phase transition from hadrons to quark matter, from nuclear matter to quark matter. These spots, as you can see, they are of size of about kilometers, okay, few kilometers. And the characteristic time scale of the system is of the order of milliseconds, okay? So if you start comparing scales, a millisecond is an infinite time, basically, compared to the QCD time scale, which is this one. And therefore, this process of phase transition, this process of changing the properties of the matter in the neutron star can be considered adiabatic from the point of view of QCD. Also, the spots, the size of the spots that would undergo these phase transitions are massive compared to the femtometer, and therefore you can consider also that this is an infinite one. So this is very similar to what will happen in the case of cosmological phase transition. However, nobody has discussed so far what will be the actual dynamics of formation of the quark matter here. And based, as I said, based on everything, this is going to be very similar to first order phase transitions in cosmology. But the difference is that now instead of cooling down a fluid, what we're doing is heating it up, or compressing it. So what I mean is, by the fact that there's been a phase transition in the neutron star merger, is that if I take the tentative QCD phase diagram, some spot of the star is going to start somewhere here in the hadronic phase, and then because of a combination of compression due to gravity and also heating up because of the shear and the collision, my matter is going to go into the quark matter and it's going to cross a possible first order phase transition line at some point. Let me call lambda, what would be the parameter that scans along this curve, okay? Which is a combination of chemical potential. So if I make a plot of the energy density of states as a function of this trajectory of matter in one of these spots that undergoes the phase transition, you would have something very similar to what I showed, because it's a first order phase transition. But now we are in the opposite side. We start with low energies, we compress and heat up our matter beyond the critical value, and therefore we enter the metastable branch. And then our system wants to do the same as in cosmology. It wants to jump to this other state, which would be the preferable one at that value of temperature and density. So let me say that in order for this paper, we didn't assume a single, any specific model. That there's, the only thing that we need is that there's an existing first order phase transition with the QCD phase diagram, and that is accessed during the merger dynamics. And the other critical assumption, of course, is what is the typical energy density scale in our system, and we took it to be this value, 1 GeV per femtometer cube, which, if you look in the literature, is what you typically expect at low temperatures inside the neutron stars. So we assume that all the typical energies in our system are going to be of this order of magnitude. Okay, so in order to determine what is going to be the peak frequency of this signal, I'll give a very crude estimation. What I need to know is what is the characteristic scale of these bubbles once they collide, how big they became, because this sets the following perturbation that would live after that and will give me gravitational waves of that wavelength. So let me start by focusing on one of the spots of the star that would undergo the phase transition of few kilometers, as I'm showing. In order By the way, the argument that I'm going to give right now is not strictly speaking correct, but it gives a very good estimation and it's much easier to understand. If anyone is interested in the actual estimation, it's a bit more obscure, but I can go into all the details you want after. So a condition that I need in order to have a system that undergoes the phase transition from here to here is that at least in this volume, during a characteristic time of the system, which is the millisecond, at least it should be able of nucleating one bubble. So what I said is that the number of bubbles that I have in my system, which is basically the rate, now I substituted the temperature by this lambda, which is a combination of temperature and density, times the volume and the characteristic time scale should give me 1. This is the condition to having one bubble in 1 millisecond. If you solve for this, this tells me that the moment in which I will nucleate is the moment in which the action of the bubble is going to be the logarithm of this. And let me stop here for a second, because this product is a comparison of scales. This lambda to the 4 is a microscopic scale. This L cubed tau is the macroscopic scale. There is a massive difference, there's a parametrically large difference between the two, and you see that the log gives you something very big. This also shows how robust is the result, because if you fail in a couple of orders of magnitude characterizing this, for example, you see that it will change this, thanks to the logarithm, in a very small amount. So the fact that there's a parametrical difference, if I change then the order of magnitude of one of the elements by a bit, there's still going to be a very large difference, and the crude estimation is still going to give me something very good. So I take the value for lambda that I said before, L is 5 kilometers and tau is 1 millisecond, and then you can get what is the time that it takes to go through the phase transition that can be estimated as what is the time derivative of this action, by the chain rule can be estimated like this, and it gives you 6 microseconds, okay? So this goes back to what you asked, that the time to go from here to here, so nucleate all the bubbles, they expand, they collide with each other, and they leave me something per turn. So that process is something that is very small compared to the millisecond. In the cosmological case, it would be very small compared to the Hubble scale. Yeah. So in these 6 microseconds, what happens is that I start nucleating a lot of bubbles. They grow to size R, which is going to be simply how fast they expand times the time they had to expand. And once they disappear, they leave me a sea of sound waves, this perturbed state, which is this state, but with perturbations of characteristic size this one. And that's going to be the characteristic frequency in which I am. Okay? So let me emphasize again, these long wavelength sound waves are long-lived and will live of the order of the millisecond. The peak is what I said, and by taking a conservative value for how fast these bubbles expand, you get that these bubbles would grow to a size of half kilometer, corresponding to a peak frequency of 0.6 megahertz, okay? Which is clearly separated from the rest of the neutron star merger spectrum because it's in the few kilohertz, okay? So this could be completely separated. Yeah. Questions so far? Okay. Okay, one thing is the frequency, another thing is can it be detected? So you need to see if you're going to have enough emission, energy emission, to see if it's going to be detected. And for that, we go to the cosmological case where years of simulations made people realize that there's a simple formula with which one can estimate how much energy density you emit due to these perturbations that live after all the bubbles have by this sea of sound waves that I call. So it's fairly simple to understand this formula. This term here squared is simply the energy density located in a fluid that is in motion. And we take again the typical energies and pressures to be this value. And the typical velocities, again, being conservative, don't take them too relativistic, you take them 0.3, for example. There's a characteristic time scale, which is how much it's the time that the radiation has to interfere with each other and give rise to an incoherent signal. And that is basically the light crossing time. Once the light crossing time has passed, the radiation has left, and it only prolongs the signal. It doesn't contribute into enhancing the signal. And then there's a factor which tells me how efficiently I transform this fluid energy into gravitational wave energy. And in cosmological cases in the literature, you can find this value. So by plugging all of that, you get a strain that looks like this in units of the distance to the neutron star of 100 megaparsec. And let me say that the detectors that are candidates to detect this are superconducting radio frequency detectors, where the next generation ones are expected to have a critical strain of about 10 to the minus 4. So then going back here, you get that this in principle could be detected if you get something in the tens of megaparsec. It's small, but there's a precedent. There's a precedent that happened on tens of megaparsecs. So given our crude estimation, this is very optimistic. The signal that you should expect is the same one that you have. You should expect is the same one that you have in cosmological phase transitions, but centered in the megahertz. It's a stochastic signal in nature, but it's localized in the sky, contrary to what happens in early universe phase transitions. And you would have all the rest of the signal to aid you to localize where it comes from and the time in which you have to look. And let me emphasize that this is the only astrophysical source in this band. And this is, strictly speaking, the only way of determining that there has been a first order phase transition in the neutron star. Because the fact that in this signal you can see that there has been a softening of the equation of state does not distinguish between a very sharp but a smooth crossover and an actual discontinuity. Okay? Well, in principle, they can be, no? Like there was in the. Ah, you mean from the bubbles? No, in principle, I don't think so. I don't think. Okay, so the work that we have to do now with holography is, well, we have a new kind of bubbles. Now we have bubbles that have baryonic number. They are not simply, there's another variable in the system. And preliminary results suggest that there are qualitative differences with respect to the bubbles that are found in the cosmological case. And holography is, again, the perfect laboratory to study them from first principles and see how they behave. In the few minutes that I have, let me emphasize that this might have an effect in the star because I'm talking about a patch that is of a few kilometers, while the star merger is going to be of around 20 kilometers. So it's not a negligible amount. So typically what simulations do is they assume that your phase transition happens as I have hadronic matter, I compress it, then I jump into a different kind of equation of state. And you incorporate that into your perfect fluid prescription by changing how does your energy density and the energy density and density of baryons compare or relate to the pressure in the system. However, now I'm saying that I will first slightly over compress or overheat, but most importantly, apart from changing the equation of state, I will not go from a fluid to the same fluid with a different prescription, but I also have some sound waves left behind that carry some energy. So the energy is redistributed between the fluid energy and then some perturbations in the body. So it would be, we're actually on track of seeing if this could actually have an effect through actual simulation. Okay. How much?
Well, we wanted 2 more minutes, but otherwise.
Then I can stop there. If anyone is interested, please talk to me.
That's it. So first question.
How many event rates of the phase one? How many events to happen by?
How many events?
How many events?
You mean how many of these phase transitions will
Yeah.
happen in a single merger?
No. There are many new how many events can be expected with use of the new detector. How many events detected?
That depends on the sensitivity that I actually reach. And it also depends on how many you can detect in the kilohertz band, right? If you miss the kilohertz band because you're, for example, LIGO nowadays, LIGO in GW17, they saw the spiral, but they missed the rest of the signal. So it could be that there's mergers right now that we are not detecting for some reason. It's true that given this sensitivity, you want mergers that are close to it. Okay, so it's not too often the ones that you're gonna get, but there's at least 1%. I don't have an exact number on which how many. What is the population of neutron stars at this scale?
How big we going to be?
The detectors,
Yeah.
something that fits in the lab. It's a cavity that is superconducting in order to avoid dissipation, and then you have a gravitational wave that passes through, and it would emit in the presence of a background magnetic field. You would excite the electromagnetic modes of the cavity.
Like
Yeah.
opportunity.
It's actually inspired in that. It's inspired in that. You excite different kind of electromagnetic modes because of the different spin, but the idea is the same. Yeah.
Other questions?
At the end, we're talking about some shortcomings of a fluid description versus we talked about the way that the fluid
Yeah.
description and how it could be improved.
Yeah.
Do you think that what you're trying to tackle here is actually like the leading order, like the leading order systematic error in current modeling? And if not, what's more important than
I'm not sure it would be something like a leading order, because what typically you have in the system is something a bit fictitious about the dynamical realization of phase transition, is that you over compress the system and then you get a mixed phase. So in general, that is not going to happen unless there's a lot of impurities. And if there's no, what you get is something completely different. And you would be comparing state here perturbed with a state here that is a mix. So right now, I don't have a clear answer, but I wouldn't say that is like what we do right now is a leading order. It's something completely.
More questions? So from my perspective, I mean, I'm interested in knowing more details about the code that you said was used in parts of the talk. Well, more specifically, the setup, I mean, you involve on null slides, is that correct? The ones.
It's characteristic formulation. So we have been going in the coordinates, and you give initial data in a slice, plus boundary data, because that's, so I forgot to mention that. Very good. So in ADS, of course, you have a boundary that is time-like, and therefore you have to prescribe boundary condition all the way here. But simply, the only thing that you're saying is what is your metric there. You fix it to be Minkowski.
All right.
Yeah. And then you give initial data here, and you have enough for both.
And how do you deal with the inside of the horizon? What do you do?
Inside the horizon, what you do is at every time step. So imagine at this zero, you give initial data at some point. We do it in such a way that we know that the apparent connection of this initial data is going to be inside. Then once you are there, what you simply do is change coordinates so that the apparent horizon lies now always at the same radial coordinate, and you just excise from your numerical grid whatever there is an epsilon behind, let's say. Yeah. So it's the only critical thing typically is that when you put initial data, you have to give some radial grid. It could be that your initial data has the apparent horizon outside, and that makes the code not able to start running. But if you do it carefully, you can always make sure that it's inside, and then you get rid of whatever there is behind. And at each time step, you keep track of it. So in general, it works very well.
How do you determine the final time? Like what's the?
That depends on the physical problem in question, but typically you don't really know, unless, typically you don't really know. I mean, you can always make an estimate what is going to be the time scale that I need to see the physics I want, or to reach equilibrium. But in general, I mean, it's very simple. What you do is you run until if you want, you fail because the key final is here. What you wanted to see, you just give this exhibition.
Oh.
So it's very fast. Yeah, in that sense, it's not crucial. You get right.
Thanks. More questions? Strictly speaking, there's 3 more minutes until it's dinner time. So, I mean, if you want to explain, if you go in 3 minutes, feel free. If not, we can leave it here.
Yeah, maybe I can talk about the Gregorian plan.
Nice.
And then we cosmic section. Well, for that, let me first say in 2 words what happens with the spinodal instability. So imagine, I was always talking about what happens if I start in this metal stable branch and then I have bubble nucleation. Okay? But I didn't say what happens if nucleation is very suppressed, for example, and then the cooling down of the universe takes me to this other branch. This has the wrong specific heat sign, it's negative, and it has an actually dynamical instability. So what happens is something, for those of you familiar with the Gregorian plan, very similar to it. The only difference is that you see that my family of states has a low energy bound that puts a cut into the family of unstable. The Gregorian plan, this will extend all the way to zero mass, to zero mass of the black state. So therefore, if you perform a simulation starting here and putting perturbations, what you see is, well, this is the initial state, this energy density as a function of 2 coordinates. This is just a homogeneous state here with some perturbations, okay? You can think of this as the apparent horizon area, for example. But it's the energy density of the duality. And then when you get this some exponentially fast process at the beginning that makes your horizon inhomogeneous, you exit the linear regime and then you merge everything into a single phase domain. So a horizon that is inhomogeneous, but it has only one interface. Okay. The reason why you stop there is because you had all these low energy horizons, low energy mass horizons that are stable. Okay. The final state looks something like this. So it's an equilibrium between this state and this state. This is like water and ice at 0 degrees. Okay. And this is just 2 passes of a horizon, one of bigger mass than the other, but same temperature. And now what we can do is tune our theory so that we make this family of black holes or states end at 0 mass. So let me explain. We can tune our theory, the parameters. So now our family of black rays look like this. So I still have a family of unstable ones. It's a critical temperature, but then there's some black brain that touches the 0 mass axis, and actually our vacuum can be singular. Okay, so no horizon geometries are singular in this theory. So here, if you run the same run, what you're gonna get is a horizon that is inhomogeneous and ends up somewhere in equilibrium with this state and this state. And if you push it a bit more, you can make this critical temperature to fall precisely with the 0 mass horizon. And then when you start here and kick the system, you're gonna make a horizon inhomogeneous. The high energy, the high mass part of the horizon will fall here, and the low mass one will fall here, which is precisely singular. Okay. So we have a way, very controlled, very regulated, of generating with just classical dynamics a naked singularity that in principle could be infinitely extended in space, depending on what in the limit of infinite size system will be infinitely extended. But the good thing here is that you have a cutoff that you can very easily modify, and you can see how the properties or how the invariants that will blow up do it as you remove these cutoffs.
Is there any way to get to use that strategy to build the naked singularity, but getting rid of the asymptotic ADS? Do it in asymptotic flat? Or is it
That's the black string. That's the regular black with it.
But yeah, okay, we have to be five-dimensional.
Yes. 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 Yeah.
So, I mean, it's the time. So, if you're happy today,
Yeah, of course.
and if there's no more questions, I suggest we leave it like that.
If you enjoyed the video, like and subscribe.